Thanks for joining. We're about to do some practice problems, which is one of the best ways that we have to help us learn. Now, if you haven't tried these problems yourself, please try them yourself first. There's this beautiful button. It's somewhere along here called pause. Make use of it. See the problem? Pause. Try it yourself. Then if you need to, you can unpause, and we can compare answers. In this way, you get engaged, you'll learn, you'll succeed. And that's what we want, your success. Let's get going. Number 1, verify. x1 is this function, 4t cubed minus 3t. I call it a function. It's a vector with entries in t. And x2 is t squared and minus 1. Our solutions to t cubed x prime is equal to 6t squared 4t to the fourth minus 3t squared x. All right. Well, this is a fun problem, right? Because there's the word verify. We don't have to derive anything. We don't have to solve anything. We just have to show something. And so, how does one verify? Well, the answer is we're going to plug it in to both sides and say, do they match? Okay, so let's start with x1. So we'll have t cubed x1 prime. Well, what is that? That's t cubed. That's multiplying by x1 prime. And so when we're taking the derivative of a vector is like a matrix, do it entry by entry. The derivative of 4t cubed, 12t squared. Derivative of minus 3t, minus 3. And we can distribute that t cubed in. And what do we get? We get 12t to the fifth and minus 3t to the third. All right, so that's if we plug x1 into the left-hand side. Now, repeat. Plug it into the right-hand side. So we have that 6t squared, 4t to the fourth, minus 3t squared times x1. All right, 6t squared, 4t to the fourth, minus 3t squared times, plug in what x1 is, 4t cubed minus 3t. Okay, so matrix multiplication. We have 6 times 4 is 24, and t squared times t cubed makes t to the fifth. So 24t to the fifth minus 12, because negative 3 times 4, and t to the fourth times t is t to the fifth. So minus 12t to the fifth. Now this is one entry. It's not a 2 by 2. It's a single entry. Minus 12, because negative 3 times 4t cubed, t cubed. And then plus 9, right, negative 3 times negative 3 plus 9, t cubed. And we add the entries. 24 minus 12, they both have t to the fifth, so that's good. That's 12t to the fifth. And minus 12 plus 9 makes 3t cubed. And what do we see? 12t to the fifth minus 3t cubed, 12t to the fifth, and 3t cubed. Minus 12 plus 9 is negative. Ha ha ha. See, that's the thing. You know they have to match, because that's the verification. And so we say, aha, these match. And that's the whole thing for x1. And see, that's one of the nice things. If you know something's off, it's like, oh, you made an algebra mistake somewhere, or you made a differentiation mistake somewhere, and just run back and find it. So this makes this type of problem free points. We like points. We like to get all our points. Well, that was an idea so nice, we do it twice, because this is x1. Repeat for x2. So we have t cubed x2 prime, right? Plug it into the left-hand side. Well, that's t cubed times, take derivatives, derivative of t squared, 2t, derivative of negative 1, 0. And what do we have? Well, multiplying in, that gives us 2t to the fourth and 0. All right, now we plug it into our right-hand side. Well, that'll be 6t squared, 4t to the fourth, minus 3t squared, and multiply that by our right hand, I got ahead of myself, multiplied by x2, and so that's 6t squared, 4t to the fourth, minus 3t squared, and x2 is t squared minus 1. All right, so carrying out the multiplication. 6t squared times t squared, 6t to the fourth. 4t to the fourth times minus 1, minus 4t to the fourth. Minus 3 times t squared, minus 3t squared. Minus 3t squared times minus 1 is a plus 3t squared. Upstairs, 6t to the fourth minus 4t to the fourth gets us 2t to the fourth. And downstairs, minus 3t squared plus 3t squared gets us no more t squared, so that's 0. And we check, and we say, aha, these match. And that's our verification, right? We just want to say, hey, it satisfies this relationship. Plug it in. So verify is plug it in and make sure that things do what they claim they do. All right, good. Number 2. Let x1 of t be t squared t plus 3 and x2 of t be t plus 10, 2. Be solutions to x prime equals a of t x. Now we don't know what a of t is, but we don't need to know that. Find the solution with x of 0 equals 20, 10. And determine the interval in which the uniqueness is guaranteed by the Wronskian. Okay, so what do we do? Well, what do we have? This is set up, now that's not explicitly stated, but it's implied to be linear. Now, linear doesn't necessarily mean that, you don't have constants here. That's okay. You can have non-constants. But what you have is this nice little matrix. So you say, okay, if I have solutions to a linear homogeneous equation, what can I do with them? I can combine them together. In particular, we can do superposition. So superposition is a way to take a few solutions and make other solutions. So our great aha is to say, or you might say, oh, there's so many things we could say. But we start by saying, well, we're going to let, in general, x of t is going to be some combination. So I'm going to add some new scalars here, a and b. Something times the first solution plus something times the second solution. And if these are linearly independent, then all solutions will look like this. And you can sort of eyeball linear independence here by just saying, do these look like multiples of each other? Because if there's only two solutions, that's the only way things could break down, and they're not multiples of each other, so that's good. Well, what do we need? Well, we need that 20, 10. Well, that needs to be x of 0. Well, that needs to be equal to a, 0, 3, plus b, 10, 2. Right, that's our initial condition. Or we get, we combine a times 0 plus b times 10, that's 10b, 3 times a plus 2 times b. And really, what does that do? Well, that's going to break into two different equations. So you have the first entry, the top entry, says that, well, we need that 20 equals 10b. And that's pretty straightforward to solve. That tells us what b needs to be, 2. The bottom says 10 has to equal 3a plus 2b. But wait a second, we know b is 2. So that tells us that 10 has to be 3a plus 4. Or, if we subtract 4, 6 equals 3a or divide by 3, a equals 2. It's okay that a and b are the same. It's okay if a and b are different. A and b are whatever they need to be. So when we put this together, that tells us the following. It says, hey, our solution x of t, it looks like 2 times t squared t plus 3 plus 2 t plus 10, 2. Now, this is a perfectly fine way to write it. I'm going to go ahead and just combine. And so we have 2t squared plus 2t plus 20. Then we have 2t plus 6 plus 4 makes plus 10. And there we go. So that is our solution, right? Check. Done. But are we done with the problem? Well, there's a word, and. Oh, more fun for us to do. Determine the interval on which uniqueness is guaranteed by the Wronskian. Now, what does that ask us to do? Essentially, the key here is to say, hey, where is the Wronskian of x1, x2 not 0? That's what we're trying to figure out. So we say, all right, well, let's get to that. So how do we compute the Wronskian? So we have the Wronskian of x1, x2. And we say the way we do it is we make a matrix. Now, how do you form this matrix? Your solutions become your columns. So t squared, t plus 3, t plus 10, 2. All right. And, well, now we start doing multiplication. Determinant, t squared times 2, 2t squared. Subtract, t plus 3 times t plus 10. Well, all right, that's 2t squared minus, and let's go ahead and distribute out. We'll have our t squared, our plus 10t, our plus 3t, that's a plus 13t, and then a plus 30. Well, if we now distribute that minus through and combine, we have 2t squared, subtract t squared makes a t squared minus 13t minus 30. Now, quadratic. And we believe in our instructors. We think they're nice people who care about us and love us. So we go into this with the optimistic point of view that they're going to give us something that will factor. So let's think about what we're trying to factor. We have a coefficient of 1, that's in front of the t squared. That's going to make life easier. So we're looking for two things that multiply to negative 30, but would add to negative 13. Well, how can you get 30? 10 and 3, but one of them is positive, one of them is negative, because I got a negative out. Now I can't get there. 5 and 6, hopeless with that. 2 and 15? Oh, wait a second. If you made it a minus 15 and a plus 2, I think that could work. Let's try it. Okay, so I think there should be like a t minus 15 and a t plus 2. Check it, right? T squared plus 2t minus 15 is minus 13t, and minus 15 times 2 is minus 30. Now, we care about where it's non-zero, so we say, well, where is it 0? And what we get are two possibilities, namely t equals 15 and t equals negative 2. So at those places, 15 and negative 2, solutions start to break down a bit. Now, what's actually happening is to say that well, let's suppose we pick negative 2. If you plug in negative 2, you'd get 4, 1 here. If you plugged in negative 2 here, you'd get 8, 2. Now think about 4, 1 versus 8, 2. They're multiples of each other. And so what happens, it says, oh, since these are multiples, then they're dependent. We lose information. So there's not enough to combine everything together. And so as you try to pass through negative 2, you basically, things converge and they split again. And so even though you know how things look before negative 2, you can't be sure how they look after. So that's why we say things fall apart. So let's be careful. We've split up our interval, well, the real numbers, into 3 pieces. So we have a negative 2 and a 15. Which piece do we care about? For that, we have to look at where our initial condition is. Our initial condition is at 0, right? Because we were talking about x of 0. Since we're at x of 0, we say, all right, well, where is 0 in our diagram? It's over here, which means our solution is good to go up until we hit our problem spots. And we cannot uniquely extend past negative 2 and 15. That's the problem, is that we can get up to negative 2 uniquely, but we can't get from there any past that without losing uniqueness. So, our second part, uniqueness is guaranteed on the interval from negative 2 up to 15. Now, we can quibble about whether to include the endpoints or not, but I would say don't include them, be safe, just because we don't know. A of t could be breaking down. That could cause problems. But for sure, we can make this conclusion. From negative 2 to 15, we are good to go. All right, and there's our second part. And so good. That part is also done. We finished this problem. Nice. Number 3. Let x1 of t be 1, 3, negative 2. x2 of t be e to the t, 2, 0, negative 3. x3 of t is e to the t, minus 1, minus 2, 2. B solutions to x prime equals ax. So this would be a case where a is a 3 by 3. We could figure out what a is, but we don't need to. And since we don't need to, we're not gonna. Because that's not part of the problem. What is the problem? Find the solution where when you plug in 0, you get 4, negative 2, negative 5. Well, maybe we got lucky. Let's try it. Plug in 0, 1, 3, negative 2. No, that didn't work. Plug in 0 here. E to 0 is 1, 2, 0, negative 3. No, no, no. Plug in 0 here. Negative 1, negative 2, negative 2. No. Okay, so none of these are the right solution. Dang it. All right, so what do? We've got to find new solutions. But how do we find more solutions? We don't even know what A is, but we don't have to because we have existing solutions. So what we'll do is we'll say, let's put them together. In other words, what we have is a nice linear, homogeneous system, right? And when we have that, we can combine old solutions to make new solutions using the principle of superposition. Isn't that just super? All right, so what do we have? Well, we say all solutions. In fact, this is the nice thing. Not just some solutions we can make, but all solutions will look like some combination of these. Well, we haven't checked linear independence, but we're going to trust. We'll trust that they gave things to us that were linearly independent. So we have 1, 3, minus 2, so some multiple of that, plus b, e to the t, 2, 0, negative 3, plus c, e to the t, minus 1, minus 2, 2. And now, what's our goal? Well, our goal is, what's the right value for ABC? ABC, it's easy as... Well, no, it's not going to be easy. It's going to take a little bit of work. All right, but it's not so bad. What we can do, what can we do? We'll start. We know what should happen when we plug in 0. So we get that 4 minus 2 minus 5. Well, that's our x of 0. And that would be plugging 0 to all 3 of these terms. Now, not a lot goes on except that these e to the zeros, they disappear because e to the 0 is 1. And while I'm here rambling, I do want to ramble about something. You'll notice that we have a repeated root because the e to the t indicates, hey, 1 was a eigenvalue twice because we have 2 e to the t's. But notice we didn't have to do any bumping. See, repeated eigenvalues don't always lead to bumps. Sometimes they do, but they don't have to. And higher up you go, lots of very interesting things can happen. And that's a story for another day because we got to finish this problem. All right, let's put this all together. And in other words, I'm going to write one single vector. We have A plus 2B minus C. 3A plus 0B minus 2C. Minus 2A minus 3B and plus 2C. All right, good. And really we get 3 equations, right? The top, middle, bottom. 3 equations, 3 unknowns. That's our bread and butter, right? That's how we're going to make our living. Okay, so let's write down our equations. And we start by writing them down, and then we start by staring at them and saying, okay, what can we do? So I'm just copying down happy equations, happy equations. All right, so those are our 3 equations, right? So the top entry is equal, middle entry is equal, bottom entry is equal. Now, what's our goal? Well, our mantra in these problems is always the same. Try to knock something out. If we can knock something out, life is good. And so we look for cancellations. And the more that we can cancel, the better. And so don't necessarily try to rush in and be like, I'm going to go crazy. I mean, you can, but I don't recommend it. So as I'm looking at this, what can I see? Well, I have 3 equations and 3 unknowns. Now the middle equation, that only has 2 unknowns, so that's good. That's helpful. And but what else can we do? Let's compare the first and third equation. So we have an A versus a minus 2A, a 2B versus minus 3B, a minus C versus a 2C. Well, notice if you doubled everything, you'd have 2A versus minus 2A and minus 2C versus 2C. That could get us some cancellation. Idea. Let's take this first equation, multiply it by 2, and then we're going to add it to this third equation. And so if we did that, what would we have? We'd have 2A and a minus 2A, which would get us to no A. We'd have 4B and minus 3B, which would get us to B, and minus 2C and plus 2C, which would, well, be nothing. And then we'd have 8 and minus 5, which would be 3. So, by looking for a way to get a good amount of cancellation, we can quickly solve for one of our unknowns. Now we know that B is 3. Nice, nice. Okay, well, let's update. Now we know that b is 3. That says that a plus 6 minus c equals 4. This, well, still says 3a minus 2c equals negative 2. And if we do it here, I'll go ahead and do it, but you'll notice something is going to happen. Minus 3b is minus 9, and plus 2c is negative 5. So here we would subtract 6, and that would get us a minus c is negative 2. Not much to do here. 3a minus 2c equals negative 2. And here, what would we have? Well, we'd have minus 2a plus 2c, and add 9 equals 4. And if you look at the first and third equation, they're redundant, which is to say, if I multiply this equation by negative 2, I get that equation. So we can just say, okay, we'll ignore that. And essentially, that's not surprising, because we've already found one of our variables. So we should get down to 2 equations, 2 unknowns. And now we're in a much better place. We are in our happy place. Say, all right, 2 equations, 2 unknowns. Now, how can we proceed? Well, let's just try a similar idea. Let's knock out something here. And there's a lot of ways you can proceed. Basically, the question, do I want to knock out the A's or knock out the C's? Let's suppose we try to knock out the C's. So I'll multiply here by negative 2. Minus 2a plus 3a, just a. Plus 2c minus 2c, 0. And then we have plus 4 and minus 2 is 2. So a is 2. All right. Well, now that's good. Now that we know a and b, we can go and plug this back in. It doesn't matter which one we plug it into. If we plug into the first one, we get 2 minus c is negative 2. If we plug it in here, we get 6 minus 2c equals negative 2. But ultimately, if you look at that, you're still going to get the same answer either way. What is c? What do you see? Here, if you swap, you'll get c is 4. Here, you can swap, and then you get 2c is 8, which is c is 4. But there should be redundancy. Like, that's the thing, is every time you solve, you can knock out an equation. So we have our A, B, C. Nice. So what do we do with that information? Well, now that we have our A, B, C, we can go back and we can say, well, A is 2, so this A is a 2. And B is 3, so okay, so that's a 3. And C is 4, all right, that's a 4. And so now there's our answer. So we can write it as 2, 1, 3 minus 2, plus 3 e to the t, 2, 0 minus 3, plus 4 e to the t, minus 1 minus 2, 2. But we can also do the following. We can put these together. And if we did that, what would we have? Single vector. Well, we'd have 2. Then we would have 6 e to the t minus 4 e to the t. So that would become a plus 2 e to the t. 2 times 3 makes 6. Then we have 0 e to the t minus 8 e to the t. And 6 minus 8 makes minus 2 e to the t. 0 minus 8. So that makes a minus 8. Got to pay attention. 2 times negative 2 is negative 4. Minus 9 e to the t plus 8 e to the t. Minus 9 plus 8 makes a minus e to the t. And there's our answer. And we're done. Woohoo! Nice. Nice. I think this might be our only time when we do 3 equations, 3 unknowns. But it's good to practice it. By the way, if you like 3 equations, 3 unknowns, there's a great class. It's called linear algebra. And it's a really important subject. And don't be scared by the title. It's good times. Wonderful things to know. All right. We'll keep moving on. Number 4. Find the general form for solutions to the system. X prime is minus 1, 3, minus 4, 7, x. All right, so we have our x prime equals ax. These always start the same way. We're going to come here to this matrix, because it's written to us in matrix form. And this is our matrix A. And we say, all right, A, you betcha, A. What are we going to do with it? We're going to find eigenvalues. So this is always the first step. So we need to find the eigenvalues of A. Okay. Dramatic pause as we write down eigenvalues of A. So, how do we find those? We're going to take the determinant of A minus lambda I. Now, that means take the determinant, and we're going to take this matrix, and on this, what I'm calling the diagonal, subtract lambda. So minus 1 minus lambda, 3, minus 4, and 7 minus lambda. All right, well, that would give us, taking our diagonal down, minus 1 minus lambda times 7 minus lambda, subtract, other diagonal going the other way, 3, negative 4. Well, okay, what is that? We get minus lambda times minus lambda is a lambda squared. And then we get a plus lambda minus 7 lambda. That makes minus 6 lambda. And then we have minus 1 times 7 is minus 7. And over here we're going to add 12. Minus 7 plus 12 plus 5. Now, does this factor? Can you think of 2 things that multiply to 5 but add to negative 6? Yeah, lambda minus 1 and lambda minus 5. And when we set that equal to 0, that says, aha, we get roots of 1 or 5. All right, good. Now, can you check this? Well, you can rederive it again. That's a check. But there's another check. So here's the idea. If you add eigenvalues, that should be equal to what's called the trace. And that's the sum on the diagonal. Okay, so let's check that. So add 1 plus 5 is 6. Does that give you minus 1 plus 7? So this trace is down this, not that diagonal, this diagonal. Minus 1 plus 7 is 6. So that's good. If you multiply eigenvalues, well, that's going to equal the determinant. Yeah, we're almost space there. Okay, so multiplying we get 5. And if we take the determinant, we get minus 7 minus minus 12. That's minus 7 plus 12. That is 5. And so that's our check, right? So here's our way we can check our eigenvalues. So, okay, good news. We are in our 2 real distinct eigenvalues. So when we have real distinct eigenvalues, what's our next step? Well, we're going to find our eigenvectors. So that's our next thing we do. And this is still going to be true even when we go into our next set of quiz problems. Because we're going to introduce some really cool things that say, oh, whoa, there's some really cool shortcuts. But for real distinct, there's not really a good shortcut. So let's do that. So how do we do it? Well, here's what we do. Let's start with 1. So we're going to start with lambda equals 1. I'm going to take this matrix A minus lambda I and put in 1. So if we do that, we get minus 2, 3, minus 4, 6. And what we're looking for is something that when we multiply that gives us 0, 0. That's our goal. Now, you can play around with it, fiddle around, do whatever you like. For me, I like something that's just quick, easy, and very predictable. So I pick a row. I tend to pick rows that look simple. The first row looks a little simpler to me. So I say, all right, I'll pick that row, and I'll just write it in reverse. So 3, negative 2. And now flip a sign. So I can flip the negative 3. Well, I flip the 3 to negative 3, or I can flip the negative 2 to positive 2. And so my claim is 3, 2. So we check, right? Negative 6 plus 6, 0. Minus 12 plus 12, 0. We're good to go. All right, so now we have found the eigenvector. So this says with lambda equals 1, we get 3, 2 eigenvector. Okay, well, this is the problem so nice. We do this twice, because we have 2 eigenvalues. So we have lambda equals 5. All right, so again, plug in 5 into this A minus lambda I. Minus 1 minus 5, minus 6. 3, minus 4. 7 minus 5, 2. Times something needs to give us 0, 0. All right, well, now pick a row, any row, doesn't really matter. And, well, let's say we pick the first row again. I mean, I said it doesn't really matter, right? And, okay, so there we go. And we write this down, and what do we have? Well, if we, again, in reverse, 3, negative 6, flip a sign. So my claim is 3, 6 works. Well, let's try it. Minus 18 plus 18. Good, that's 0. Minus 12 plus 12, that's 0. Now, you might notice something, though, about this particular answer. 3 and 2, that's great. No common divisors. But 3 and 6 have a common divisor of 3. Now, in practice, here's what I recommend. Divide out, right? Eigenvectors are not unique. You can scale. So scale to make the numbers easier to work with. So I just like to do that out of habit. It's not technically required at all, but oftentimes you'll find it's better to simplify for later computations. And it's good to get into the habit. So what I'm going to do is I'm going to scale by 1/3. And so if you like, divide out by 3. So that's a 1, 2. And I wrote lambda equals 1. I should have written lambda equals 5. Okay. So now we have our eigenvalues, eigenvectors. And here's the thing to remember. Each pair gets a solution. So this would be the solution, e to the 1 times t. Right? There's our lambda, and then our eigenvector. Here, we get e to the 5 times t. Right? There's our lambda, eigenvector. And since we're after a general form, we've now found 2 solutions. How do we find the general form? Superposition. Woohoo! We say that word a lot. It must be really important. Yes. Yes, it is. So some constant a, e to the t, 3, 2, plus some constant b, e to the 5t, 1, 2. And that's our general form. Ah, good job, us. Good job, us. Number 5. Find the general form for solutions to x equals 5 minus 4, 3 minus 2, x prime. Now, we have a bit of a quandary here. You might say, oh, well, let's just find the eigenvalues, eigenvectors, and proceed. But notice, where is the x prime? The x prime is attached to the matrix and not to the x, right? We want the matrix over here on this side. So we're like, oh, darn it. How can we move it? Well, there's a hint, and the hint is a very good hint. It says, oh, if you have a matrix, you can multiply it by the inverse, and you get the identity, also known as the thing that acts like 1. So, okay, all right. So let's take this particular matrix here, and a question. How do we get its inverse? And so there's a shortcut here. We'll just, as a reminder, we'll put it in. If you want to take A, B, C, D inverse, you take 1 over the determinant, which is AD minus BC, and then you swap the entries on the diagonal, so it's D, then A, and then you flip the signs on the off diagonal, minus B, minus C. So that's what we need to get to. So we say, okay, so the inverse here, we'll take minus 10, 1 over minus 10, and then minus 12, minus 12. Then we're going to swap the entries on the diagonal, and then we're going to flip the signs in the off diagonal. All right, that's our inverse. Okay, well, minus 10 plus 12 is a half. So we have that this is a half, minus 2, 4, minus 3, 5. Or if you like, we can put the half through, and we'll get minus 1, 2, minus 3 halves, 5 halves. Now, why do all of that? Well, here's the reason. We can start with our original equation. I'm going to flip the sides. 5 minus 4, 3 minus 2, x prime equals suspicious gap x. There's a reason I put a suspicious gap in there, because we're going to do something to it. Now, if we were channeling our inner, like, oh, if these weren't matrices, these were numbers, we say, let's divide out. So we're going to do that. But what does divide out mean? Divide out means multiply by the inverse. Right? If I want to divide by 2, multiply by the inverse of 2, multiply by half. So we've actually computed the inverse already. So we're going to take both sides and multiply it by the same matrix. Now there's a great philosophy that says if you start with things which are equal and you do the same thing to them, you have to end with things which are equal. That's how a lot of math gets done. And over here, well, if you check, you get minus 5 plus 6 is 1. 4 minus 4 is 0. Minus 15 halves plus 15 halves is 0. And 12 halves minus 10 halves is 2 halves, which is 1. By design, not a coincidence, this is your identity. And if you take the identity times anything, you get back the thing. So, really, our problem here should have been written as the following. X prime is minus 1, 2, minus 3 halves, 5 halves, x. All right, now this is not our solution. This is just our restated problem. But we've restated it in a way which we like. In other words, in a way that we're like, okay, now we have a plan. So, good. Well, what's our plan? Since we have x prime equals matrix x, then our plan always says, step 1, find the inverse. Oh, sorry, not find the inverse. Find the eigenvalues. I have too much inverse on my mind. Okay, so we're going to find our eigenvalues. So Here we go. Take the determinant, minus 1 minus lambda, 2 minus 3 halves, and 5 halves minus lambda. All right, so this would be, minus 1 minus lambda, 5 halves minus lambda, subtract 2 times negative 3 halves. And we just start expanding here. So we get a lambda squared. And then we're going to get a plus lambda and a minus 5 halves lambda. So that would make a minus 3 halves lambda when we were done. And then we're going to get a minus 5 halves. But here we have a plus 6, right? Because the 2's, plus 3, 6 halves. So we have a minus 5 halves plus 3, which makes plus 1 half. Now at this point, you're probably like, I'm not as comfortable with this kind of factoring, Steve. Well, we can pull out a half. Then we get a 2 lambda squared minus 3 lambda plus 1. Okay, now what? Well, we need to have, if it factors, and we believe that they gave us something nice to factor. 2 lambda squared says we need a 2 lambda and a lambda. 1 says we need a 1 and a 1. So not a lot of choices, right? We don't have to think about which one gets the 1. They both get the 1. Since this is a positive and that's a negative, if it factors it at all, it would have to be that. There's no other option. So if this doesn't work, we've got to go to quadratic formula. So let's see if it works. 2 lambda squared, check. Minus 2 lambda minus lambda is minus 3 lambda, check. And minus 1 times minus 1 is 0. Life is good. And so we end up with lambda is a half. Lambda is 1. All right, well, we can do some quick checks. If we add these together, we get 3 halves. If we add the entries on the diagonal, we get 3 halves. Good. If you multiply these, you get a half. If you multiply these, we get minus 5 halves plus 6, which is a half. So these are right. I'm going to make a little comment here, which is to say, if you flip these upside down, so in other words, the 1 half becomes 2, the 1 becomes 1. 2 and 1 are the eigenvalues of this matrix up here. Not a coincidence. Not a coincidence. But that's the story for a different class. That's not our story to tell. All right. Well, let's resume our regularly scheduled problem. We have distinct eigenvalues, distinct real eigenvalues, which means we need eigenvectors. Let's start with 1. All right, so if we start with 1, no reason why, just pick one, doesn't matter. And, okay, so we're plugging in lambda equals 1. We'll get minus 1, minus 1, that makes minus 2, 2, minus 3 halves, 3 halves, and we're looking for multiplying something and get out 0, 0. All right, can you see something? I actually see something. 1, 1, right? Right, because minus 2 plus 2, minus 3 halves plus 3 halves. 1, 1 is very common. You say, oh, okay, all right. So we end up with lambda equals 1, goes with eigenvector 1, 1. All right, well, that still leaves us with another one. Lambda equals a half. Okay. So minus 1 minus a half. Minus 3 halves, 2. And we have minus 3 halves. And then we get 5 halves minus half, that's 4 halves, or 2. Okay, well, now what? Well, maybe not quite so fast, right? But we can just do things like, if we write this in reverse order, 2 minus 3 halves, and then just flip a sign. So I claim 2 3 halves works. And let's check. We get a minus 3 plus 3 minus 3 plus 3. And, well, if you don't like fractions, we could say, let's scale. And we'll scale by 2. So that would give us 4, 3. So for lambda equals 1/2, we get 4, 3. Now, what do we have? Well, each one of these gives us a solution. So for the value of 1, we get the solution e to the 1 times t, 1, 1. Right? E to the eigenvalue t times eigenvector. For the value of half, we get e to the 1/2 t, 4, 3. So these are the two solutions coming from our eigenvalue-eigenvector pair. And finally, to get to general form, we superposition. So some multiple of the first plus some multiple of the second. And we're done. That's the general form. General form is just like all possible solutions. And so our plan, put it in a way that's, follows the basic formula. Given matrix, find eigenvalues. Given eigenvalues, find eigenvectors. Given eigenvalue eigenvectors, find solutions and superposition them. When you say it like that, it sounds like there's a lot to these problems. Well, there's a bit, but they are methodical. Follow the method, and you'll be great. You'll be wonderful. Number 6. Find the solution to the system x prime equals 3, 5, 1, minus 1x with x of 0 is 8 minus 2. All right, so now we have an initial value problem. Okay, cool. Okay, so what do? Well, we start with our matrix here. We'll call it A. And first step is figure out what the eigenvalues of A are. And so we say, okay, what are the eigenvalues of A? We're going to take the determinant of A minus lambda I. So that's the determinant 3 minus lambda, 5, 1, minus 1 minus lambda, which would be 3 minus lambda times minus 1 minus lambda, subtract 1 times 5. We expand, minus lambda times minus lambda, lambda squared, then a minus 3 lambda, a plus lambda, makes a minus 2 lambda. Then we have a minus 3 and a minus 5, which would make that minus 8. Okay, so what are we looking for? Two numbers which would multiply to negative 8, but would add to negative 2. Can you think of two numbers that do that? Yeah, not a lot of ways to write 8 as a product. 1 times 8, hopeless. 2 times 4, I see some hope. Let's try lambda minus 4 and lambda plus 2. Does it work? Lambda squared, check. 2 lambda minus 4 lambda is minus 2 lambda and minus 8. Nice. All right, now when we set this equal to 0, that says, we have two possibilities, two eigenvalues. So our eigenvalues are lambda equals 4 and lambda equals negative 2. Distinct, real eigenvalues. So once we're in that setting, we say, all right, well, that says we're going to find eigenvectors. So hopefully we're getting good at this. Okay, so eigenvectors. Lambda equals 4. Well, we're going to put in 4 in for lambda. 3 minus 4 is minus 1. 5. Then we have 1. And minus 1 minus 4 is minus 5. And we're going to multiply that by something to get out 0, 0. So the question is, what's the something? What do we put here? And lots of ways to get to the answer. But, it doesn't take too long to figure out something that works. I pick a row, doesn't really matter. They're very similar. Let's say I pick the first row. And I say, all right, write it in reverse order. 5 minus 1, and flip a sign. So I flip the sign downstairs. So I claim 5, 1 will do it. Well, does it work? Let's see. We get minus 5 plus 5, and 5 minus 5. It did work. Nice. Okay, so that says we get the following pair, right? So for lambda equals 4, we get 5, 1. Now we're going to do that again with lambda equals minus 2. So lambda equals minus 2. Plug in minus 2. 3 minus minus 2 makes 5. 5. And here we get a 1. Minus 1 minus minus 2 is 1. And we have to multiply that by something to get out 0, 0. All right. Well, can you see something that works? Well, pick a row. Hey, that second row, that looks pretty nice. You probably even see it without me going through the whole process, right? Pick a row, flip an entry. So I claim 1 minus 1 does it. And you can work it out, right? 5 minus 5 is 0. 1 minus 1 is 0. Okay, so that says for lambda equals minus 2, go with 1, negative 1. All right. Now, with that out of the way, we can say, what's our general form? Okay, so we found eigenvalues. We did eigenvectors. We moved to general form. And, well, we get that it looks like x is some multiple times e to the 4t, 5, 1, plus some multiple e to the minus 2t, 1 minus 1. Okay, so that's our general form. So, progress. Except we're not done, because the problem isn't about finding a general form, it's about finding a specific solution satisfying some initial conditions. But finding the general form is a step to doing that. Now what do we do? Well, our new goal, we need to solve for a and b. So that's our next step. So how do we do that? Here's where our initial conditions come in, because we haven't used the initial conditions at all yet. We have that 8 minus 2, so here's our vector. That is our x of 0 is equal to, plug in t equals 0. A, and e to the 0 is 1. It's a very convenient number. So a times 5, 1 plus b, e to the 0 is again 1, 1 negative 1. Or we get 5a plus b and a subtract b. Now this leads to two equations, two unknowns, right? Set the top equal, set the bottom equal. And we just have to go and work that out. Now, I say just, we never, take anything for granted, but 5a plus b equals 8, and a minus b equals minus 2. Hopefully, if we've lived a good, clean algebra life, something nice will happen, and I can't help but notice we have a b and a minus b. Nice. So if we straight add, we get 6a, no b's, equals 6, which says a should be 1. Okay, throw that in. This is one of the equations. 1 minus b equals negative 2. Swap those around, and we get that b equals 3. So there's our a and our b. So we're almost done. What do? Well, we're going to put these values for a and b in for a and b. So we're going to go from our general solution to a very specific solution, but it's the specific solution that we're trying to find. So we're almost there. Our last hurrah. We have that our x is 1 e to the 4t, 5, 1, plus 3 e to the minus 2t, 1 minus 1. And I'll go ahead and push this into a single vector. This is perfectly fine. This is the correct answer. I'm not saying you have to do this next step. This is a fine answer. But I'm going to go ahead and do one more thing and say this is 5 e to the 4t plus 3 e to the minus 2t and e to the 4t minus 3e to the minus 2t. And there we go. That is our x that satisfies this differential system and has those initial values. Okay, so recap. Find eigenvalues, find eigenvectors. That gives you solutions. Superposition to find general form. So far, so good. Use initial conditions to solve for coefficients. Put those initial conditions into general form. Get the answer. Lots of small steps, but each one of them is doable. Don't be overwhelmed by big processes. Big processes are lots of little processes put together, and you can do them. You can do this. Number 7. And before we go too far into this problem, I'm going to go ahead and just say, of all the quiz problems over the whole semester, this one I think is the most interesting. It could arguably be the most non-trivial or most challenging. But once you see the idea, it's a beautiful idea. So don't get nervous. Follow along for the ideas and practice it. Okay, so here's what we have. We have that x1 is e to the t times 2 cosine 4t plus sine 4t and 3 cosine 4t minus sine 4t. We're told that's a solution to x prime equals ax. Now what is a? They didn't give it to us. Can we find it? We can. Are we going to do it? We are not. Find the solution with x of 0 is 1, 9. Okay. Now, there's certainly a challenge here. We don't know what a is, and there are ways to find it. Better ways we'll know in a week. But how do we find the solution? Now, maybe they gave it to us. Let's see. Did they give it to us? Plug in 0. E of 0 is 1. And sine of 0 is 0. Cosine of 0 is 1. So we get 2, 3. And that is not 1, 9. So we have a problem. How do we overcome this? Because we can't do superposition yet. We just have one solution. So we have to get a second solution. But we don't know A. So how can we get a second solution if we don't know A? All right, so let's sit back for a second and look at this. What kind of solution is this? What do we see? Well, notice what we have. Cosines and sines. When we see the sine, it opens up our eyes and tells us, oh, this means complex roots. That's right. We saw the sine. So, in particular, we say, aha, A has complex roots. Now, that's part of the story. We could even figure out what the roots are. They're 1 plus minus 4i. We know it's the 1 because the coefficient of t up in the exponential part is 1. The 4i is because the inside of the cosines and sines are 4. Don't worry about that part, though. That's not what we're going to focus on. So what we can do is we say, look, it turns out that when we have these kinds of solutions, they come in pairs. So let's think about our current solution. Our current solution, I'm going to rewrite it. I'm going to pull it apart. So I'm going to write it as e to the t cosine of 4t times 2, 3, and then a plus e to the t sine of 4t times 1 minus 1. Okay, so remember that. I'm going to give myself some room because we're going to do some little magic in a few minutes. Now, let's go back and say, what did we do when we had complex roots? Well, what we did is we said that corresponds to e to the a plus bi times t. That was, we're writing our solution. And then we said, oh, and our eigenvector is you had an a, and okay, how should I write my a? I'll write it this way, a, and plus I, b. Right, this is our eigenvector. All right, and then we said, idea. We're going to write this out and do what we did when we had our old setting back in the old days, which is to say, when we had complex roots, we grabbed the real parts and the imaginary parts, and that helped us form a new solution. And it's like real recognizes real, imaginary recognizes imaginary. So we have our a plus I, b. So right now, everything below here is going to be generic. But we're going to come back and talk about how we get to our more information. So if you're trying to say, wait, how does that fit into here? This is completely generic. All right. So when we do the real, we get e to the at cosine bt times this first piece. So e to the at cosine bt times this eigenvector a, our piece of an eigenvector, I really should say. And then the other real piece comes from imaginary times imaginary. I squared is a minus 1. So minus, and then we have e to the at sine of bt times b. All right. So there is solution number 1. And then, okay, plus I. Okay, then we have e to the at cosine bt times b. Okay. Plus e to the at sine of bt times a. All right. So here is, for lack of a better term, I'll say solution number 1 and solution number 2. Now, what do we do? What do we do? Well, we say, gosh, this looks a lot like that. And so we're like, oh, let's use that. Okay, so if we did that, let's update this. I want to make this match that. So we have e to the at cosine bt times a. So this part right here is a. Now I want to make a minus. So I'm going to change this plus to a minus, and I'm just going to flip the signs on the inside. That's allowed, right? So I'm putting a minus in. So minus e to the at sine bt, and this part is b. So there's first solution. What's second solution? Now we're just going to write down. So our second solution, according to this, is we say, that would be e to the t cosine 4t times b? Well, in this case, b is minus 1, 1. Just copying down, minus 1, 1. Plus e to the t sine 4t times a, 2, 3. Now we have two solutions. That's the right number. And these are different solutions. Like if you plug in 0, 0, you get different vectors, which means they're independent. Now, there's a couple of things you might ask. It's like, wait, what? Does this always work? Because how do we know that this came from a particular expression like this? We don't. But it came from things that looked like that, and came from things that look like that in a linear way. And what we're doing here is we're basically doing things in a linear rearrangement of things. And so it will work. This will always work in this particular setting. It's a very, very narrow thing. But essentially what we're testing on here is, do you recognize, I see one solution. I recognize the form in that solution. That gives me form in the other solution. That gives me solution number 2. Okay, so with that out of the way, that's the hard part. Now we get to the fun part. We have two solutions. So what do we have? Well, that says that in general, if we want all solutions, so the general form, we're going to say x is some multiple, work my way up through the alpha values, c x1 plus dx2. Now, we are after a very specific solution. So let's go ahead and work through that. So we're going to plug in t equals 0. And so we get that 1, 9, that's x of 0. That's equal to c times x1 of 0. Now I plug in 0 into the sign, you get that goes away. E to the 0 cosine 0 is 1. So that's a 2, 3 plus a d. And again, plug in 0, that goes away. E to the 0 and cosine 0 is 1. And so you get minus 1, 1. Or you get, if you extract your two equations, 1 is equal to 2c minus d. So this is read along the top. 9 is 3c plus d. And what can you do? Well, if you add those two together, you get 10 equals 5c, and the d's cancel. Or c equals 2. Now that you know c equals 2, 1 equals 4 minus d, or d equals 3. All right, good, good. And we can double check. No, 4 minus 3 is 1. And here we get 6 plus 3 is 9. So now we had our general form. We solved for our coefficients. So our last thing to do is just put it all together. Okay, so our put it all together. We have that x is equal to c, which is 2 times x1. And x1 we can write in that way, but we'll go ahead and do it here. So we have 2 times e to the t cosine 4t 2, 3 minus e to the t sine 4t minus 1, 1 plus 3 times e to the t cosine 4t minus 1, 1 plus e to the t sine of 4t 2, 3. And we can just squish it all together. And if we do that, well, what do we have? We'll work our way on the top. We get 2 times 2, so we should put that as 4. 4 e to the t cosine 4t. Here, minus 2 times minus 1 makes a plus 2 e to the t sine 4t. 3 e to the t cosine 4t minus 1. So that's minus 3 e to the t cosine 4t. Then we have 3 times 1 times 2 is 6 e to the t sine of 4t. Bottom, 2 times 3 makes 6 e to the t cosine 4t. Then we have a 2 times a minus times a 1, that's a minus 2 e to the t sine of 4t. 3 e to the t cosine 4t times 1, so plus 3 e to the t cosine 4t. 3 times 3 times 1 makes 9. So we have a plus 9 e to the t sine 4t. And finally, and these up on the inside, 4 minus 3 makes 1. So e to the t cosine 4t. A 2 plus a 6 makes 8 e to the t sine 4t. 6 plus 3 makes 9 e to the t cosine 4t. Minus 2 plus 9 makes 7 e to the t sine 4t. And we're done. Whew. Oh, thank goodness, because we ran out of paper. But yeah, there you go. There you go. So the heart of this problem is really to understand, how do solutions look when you have complex roots? Even before that, it's taking a second to say, oh, I recognize that I have complex roots. And then I say, how can I take one solution and make a different solution? You know, taking the real and making it look like the imaginary, or vice versa. So that's how we can extract a second solution. Even though they only gave us one, we could use that to make 2. And then once we had that, we then just do our typical, take our general form, solve for the coefficients, and work it out. So there's a bit of work. You know, let's not kid ourselves. A bit of work goes into solving this. But it is solvable. And once you see it and you practice it, you can do it. So keep it up. Keep doing the work. It's going to come. I believe in you. All right, let's keep going. Number 8. Find the solution to the system x prime is 2, 8, minus 1, minus 2, x with x of 0 equals 3, 2. All right, well, let's do it. So what do we have? What do we have? First step, always when we have this, we see our matrix A here, we find the eigenvalues of A. And, all right, what are our eigenvalues of A going to be? Well, we take our determinant of A minus lambda I, and that is going to be 2 minus lambda, 8 minus 1, minus 2 minus lambda. And okay, so that's 2 minus lambda times minus 2 minus lambda, subtract minus 1, 8. And that would give us minus, well, let's start with the lambdas. Lambda squared. We have a minus 2 lambda and a plus 2 lambda, which cancels. That's nice. And a minus 4 and a plus 8. Minus 4 plus 8 makes plus 4. Well, you see how to factor that one? Well, not so clean, is it? But it's not too hard to see what to do, because we can just rearrange and say, oh, hey, this is really lambda squared is -4, or lambda is plus minus 2i, right? Because to get rid of the square, we take a square root. And when we see a square root of -1, we say, oh, that looks like I, because I is that, the imaginary thing that says you look like I squared is -1. Okay, so we're dealing with something complex. Well, now that we have a complex thing, next week we'd have a much better way to do this problem, but that's next week. And this week we have one choice: to move forward and say, okay, next step for our current understanding. Oh, we're going to look back on this problem and say, we could have done this so much faster. We're going to find eigenvector. We only need one. And what I recommend is you use the positive. So we're going to go lambda equals 2i. So no, only need one. Okay, and the reason we only need one is because we're in complex. Things come in pairs. Once you understand one eigenvector, the other one is right there for us to grab. So we have, put in lambda, we get 2 minus 2i, 8, minus 1, minus 2, minus 2i. We have to multiply that by something and get out 0, 0. But we don't have to wander too long. We can figure it out pretty quickly. We say, pick a row. Well, there's a very convenient row right there. Write it backwards. Okay, writing it backwards. Minus 2, minus 2i, minus 1. Flip the sign on one of the entries. All right, flip on the first. So 2 plus 2i and minus 1. And done. There's our eigenvector. And this eigenvector, for what we're going to do next, it's very convenient to say pull it apart. So I'm going to write it as the real pieces, 2 minus 1, plus the I times the imaginary pieces, 2, 0. Okay. Good. Good. Now, what comes next? Well, now we're going to find our solutions. And so for this, I always say, hey, it's e to the a plus bi times t. And then we're going to take the pieces of our eigenvector, the real and the imaginary parts. All right. And, okay, so what does that give us? Well, in our case, notice that a is 0. And so it's really e to the 2it. So this becomes cosine 2t plus I sine 2t. And we already pulled this apart. So we have 2 minus 1 plus I 2, 0. Multiply out. Reals and imaginaries. So we get cosine 2t, 2 negative 1, minus, because you have that I squared, sine of 2t, 2, 0. Okay, that's 1 plus I, and then we have cosine 2t times 2, 0, plus sine of 2t, 2, negative 1. And now we're like, aha, because things come in pairs, eigenvalues come in pairs, eigenvectors come in pairs, we can grab the imaginary parts and the real part. So here's our real part, here's our x1, here's our imaginary part, there's our x2. And so, where are we at? Well, now we can write down the general form for solutions. And we say, in general, our problem looks like x is some constant c times x1. Well, I'm going to go ahead, compress this down. So that's 2 cosine 2t minus 2 sine 2t. And then we have a minus cosine 2t and a 0. Plus some constant d. And here we'll get a 2 cosine 2t of 2 sine of 2t, a 0, and a minus sine of 2t. We just need to solve for c and d, and then we'll have our answer. So, we're close. Let's quickly recap what we've done so far. Had eigenvalues, they were complex, we grabbed one eigenvector. We said, okay, eigenvalue, eigenvector, we can extract two solutions. Grabbing the real part, grab the imaginary part. So now we have our superposition. We're ready to move in and say, initial values. So let's do that. We can do that down below. We'll do it down here. We have a little bit of space down there. When we plug in 0, we get 3, 2. That's x of 0. Well, that's equal to c. Cosine of 0 is 1, sine of 0 is 0. So that's c times 2 minus 1 plus d times 2, 0. Right? And, or, if you like, that is, 2c plus 2d and a minus c. Okay, good. And, almost there. Well, we have a system of equations. We get that 2c plus 2d is equal to 3, and we get that 2 equals minus c. Well, I can solve for that equation pretty quickly. We say, any combination of those noises, and we get that c is minus 2. Well, that tells us that minus 4 plus 2d equals 3, or 2d equals 7, or d equals 7/2. Okay, so there we go. So now we've solved for c and d. And we come in and we say, all right, so c, this will be minus 2, and d, this will be 7/2. And we're in the home stretch. So last thing we can do is, now that we have all these values, we plug them in. And let's go ahead and write this as one nice big expression. We have minus 2 times 2 cosine 2t, so that's minus 4 cosine 2t. Minus 2 times minus 2 makes a plus 4 sine of 2t. Then we have a 7/2 times 2. That would be a plus 7 cosine 2t. And a 7/2 times 2 makes a plus 7 sine of 2t. Then downstairs, we have a minus 2. That makes a plus 2 cosine 2t. Then we have a 7/2 times a minus 7/2 sine of 2t. Or, all together, minus 4 plus 7 makes 3 cosine 2t. And then 4 plus 7 makes 11 sine of 2t. And then downstairs, 2 cosine 2t and minus 7/2 sine 2t. And there we go. We did it! We solved it! Woohoo! Nice! Right? Trust the process. The process works. Just got to keep going, and it'll carry you through. All right. Good. Well, let's keep going, right? We got this. Number 9. Find the general form for solutions to the system x prime is 2, 1, minus 1, 4, x. All right, well, we're pretty used to it, right? We have here our matrix A, and step 1, what are the eigenvalues? It's always the same thing. When we see that matrix, we're like, I wonder what those eigenvalues are, because that will tell us how to approach solving the problem. So we're going to take the determinant, a minus lambda I. So that's our 2 minus lambda, 1 minus 1, 4 minus lambda, which would give us 2 minus lambda times 4 minus lambda, subtract minus 1, 1. Sorry, dramatic pause. Just checking something really quick. Lambda squared minus 2 lambda minus 4 lambda is minus 6 lambda. Then we have a plus 8 and a plus 1 makes plus 9. And that, well, I think that factors. It's a perfect square. Lambda minus 3 squared. Which means what? We have repeated eigenvalues. Okay, cool. Now that puts us into sort of a new territory. And when you have a 2 by 2, if you have repeated eigenvalues and your matrix is not boring, and what do I mean by boring matrix? Boring matrix would be 3, 3. That would be a boring matrix. This is not a boring matrix. That says we have troubles, my friend. Okay, so let's see what I mean by that. So, let's start with an eigenvectors. We only have one eigenvalue, so that should hopefully make things simpler. And if we plug in our lambda equals 3, we get 2 minus 1, that's minus 1, 1, minus 1, 1. We have to multiply that by something and get out 0, 0. All right, well, can you see something that does that? I think we can. Yeah, 1, 1. That does it. You can write the first row in reverse and flip the sign, and just check minus 1 plus 1 minus 1 plus 1. And there's just one eigenvector. Okay, so what's our problem? We don't have a second eigenvector. So it's not necessarily repeated eigenvalues, it's a shortcoming of eigenvectors. However, that shortcoming of eigenvectors can only happen during repeated eigenvalues, so that's why they're often associated together. So how do we solve our gap? Well, before we continue, we will make a note. We get a pair, right? We get 3 for the eigenvalue and 1, 1 eigenvector, and so we get our solution, e to the 3t, 1, 1. So, what would we like to do? Well, the moral is we want to bump. And if we call this a vector v, just as a reminder, what we're getting here is that our first solution should look like e to the lambda t times v. How do we find our second solution? Well, what we do is we come back to this equation, but now we say instead of doing that, we move this 1, 1 across and say, all right, our goal now is to say, here is v. Right, this is our v. Now we've moved it across. We're looking for w. Find some nice vector that we can put here. And don't try to be complicated, try to be simple. And because it's 2 by 2, a multiple of the column will always work. And there's lots of ways to do it. I think I'm just going to grab the second column, which looks like 0, 1. And you should check, right? 0 plus 1, 0 plus 1. Good. And now, why do we do all that? Well, the punchline here is that second solution will look like t e to the lambda t times v plus w times, plus e to the lambda t times w. So it's like kind of like bump, but you have a small correction term. So for us, that says, okay, what does our second solution look like? So our second solution looks like t e to the 3t times 1, 1. So we take our first solution and multiply by t, but then we add a correction term, e to the 3t times this w, 0, 1. So those are our two solutions. So this is how you get solutions when you have repeated eigenvalues. Now we can put these together and do superposition. And if we do all of that, we get the following. X is some constant, I'll say a e to the 3t, 1, 1, plus some constant b t e to the 3t, 1, 1, plus e to the 3t, 0, 1. And we're after general form, so we don't have to solve for initial conditions, and so life is good. That's it. And you might say, that's not so bad. I just got to remember a few things. Is there a faster way? Yes. Do we know it? We will soon. We will soon. So be patient. We're going to see a really slick way to do these types of problems. All right, good. Almost done. Almost done. Number 10. We're given that x1 is e to the minus 2t times 1 plus 3t 2t is a solution, x prime equals ax. And we're asked, find the solution where when we plug in 0, we get minus 1, 4. Now, maybe they just gave it to us. If you plug in 0, that does not give minus 1, 4. Okay, so they did not give it to us. All right, no worries, no worries. So how do we find it? Well, what we need to do is we need to understand, hey, what is being told to us? We are given one solution, so to find general solutions, we need a second solution. So let's stare at this for a second. And we ask ourselves, is there anything about this solution which makes us say, what do you think? Is there anything making us say, I see something. I see t's here. And say, well, what does that mean? Well, one thing is it tells us that we could have written x1 in the following format. T e to the minus 2t times 3, 2 plus e to the minus 2t times 1, 0. All right. How does that help us? Well, when we see that t, we say, oh, hold on a second. That means we did a bump. In other words, a repeated eigenvalue. Because we're in 2 by 2, the only time we can bump is if we see a repeated eigenvalue. And we're like, oh, wait a second, hold on. When we have repeated eigenvalues, we know something about what answers have to look like. And in particular, we say, well, answers look like the following. They'll look like you have your e to lambda t v, and then you'll have t e to lambda t v plus e to lambda t w. So these are your two solutions when you have repeated eigenvalues. So what do? Well, we say, great, this is perfect. Because we say, aha, this is our V and this is our W. And so we say, okay, so they gave us, this is what they gave. And so here's our other solution. And so we're like, perfect, that makes it super clean to find our other solution. So our other solution is going to be e to the minus 2t, 3, 2, right? Don't need the t, so it's e to the lambda t v. And so now we have our two solutions. And so we're in great shape. We now have general form. And so our general form has the following. It'll look like some multiple a times this, I'll write as e to the minus 2t, 1 plus 3t, and 2t, plus some multiple b, e to the minus 2t, 3, 2. So with that, now we just have to solve for a and b. Okay, well, we can make progress in that. So what do? Well, we plug in. We have some initial conditions. So we're told that minus 1, 4 is x of 0. And that would be a. E to the 0 is 1. When you plug in t equals 0, you get 0 for 3t and 2t. So 1, 0. Plus b, e to the 0 is again 1, 3, 2. And that leads us to two equations, right? Minus 1 is a plus 3b, right? Minus 1a plus 3b. 4 is 0a plus 2b. Well, that's a pretty quick equation to solve for. That tells us that b needs to be 2. Well, now I know that b equals 2. We get, okay, minus 1 equals a plus 6. Right? 2 times 3. Or a is minus 7. Great. Well, now we know what a is. What do? Well, just plug it in. Right? So we know that a is minus 7 and b is 2. And so our last thing to do is to write down our answer and maybe do some cleaning up. Okay, so we have that x is equal to minus 7 e to the minus 2t, 1 plus 3t, 2t, and then plus 2 e to the minus 2t, 3, 2. We can put this all together. Everything has an e to the minus 2t. We'll leave that on the outside. Minus 7 minus 21t, and then plus 6. Here, minus 14t plus 4. Or e to the minus 2t times minus 7 plus 6 makes a minus 1 minus 21t. And then we have a 4 minus a 14t. And we're done! Woohoo! We did it. We did all our problems. It took a while, but we succeeded. Good for us. Good for us. All right. Now, there are some pretty straightforward ones and some pretty not straightforward ones, right? A few that were a bit of a challenge that tested, do we understand what's going on? But a lot of the problems follow the same formula. You've got your matrix, you find your eigenvalues, and that will tell you what to do. Find eigenvectors, combine in different ways. A lot of what we do now will become simpler when we have a better tool called matrix exponentials, So don't panic. A better way is coming. But we need to get through the process now to appreciate what comes next. Thank you for being here. Thanks for putting in the work. I am grateful that you put in the time and energy that you do. It will pay off for you. The more that you learn, the more that you'll see. So keep it up. Keep it up. You can do it. All right. Take care. Bye.